The universe is going to die, not dramatically, not in fire, just quietly. Over an incomprehensible stretch of time, it will run out of things to do. The last star will go dark. The last black hole will evaporate. And then, perfect silence, forever. That was the answer. Then a Nobel Prize-winning physicist looked at that silence and said, "Wait, that is not an ending. That is mathematically identical to a new Big Bang." Roger Penrose believes our universe is one link in an infinite chain, and that the radiation passing through your body right now is older than time itself. If you are new here, welcome to Sundown Science. Get comfortable. Subscribe if this is your kind of thing. You are going to want to stay for this one. Part 1. The ending that should have been final. Picture the last night the universe ever has. Not a night like ours, no stars overhead, no planets turning through their slow ellipses, no light of any kind falling on any surface anywhere, just cold, just distance. Just the long, patient nothing that physics has been building toward since the first fraction of a second after the Big Bang. The last red dwarf burned out so long ago that the number of years since then has more digits than there are atoms in the observable universe. The last black hole finished evaporating, and we will get to exactly how long that takes, because the number is almost insultingly large, and after it went, there was nothing left to structure space at all. No gravity wells, no hotspots, no condensation points. Just a near-uniform bath of photons and neutrinos drifting outward through a universe that has been expanding for so long, at so great a rate, that the distance between any two particles is functionally infinite for all purposes that matter. This is what physicists call heat death, and for most of the 20th century, it was considered the final answer to the question of what happens at the end of everything. Not an explosion, not a collapse. Not a dramatic finale of any kind, just a quiet, absolute, mathematically impeccable fade to nothing. The universe runs out of usable energy. Entropy, the tendency of systems to move from ordered states to disordered ones, reaches its maximum value. And once entropy is maximized, once every possible configuration of matter and energy has been fully scrambled into its most probable arrangement, nothing can happen anymore, ever. Physics does not stop. The equations still technically hold, but nothing changes because there is nothing left to change. That is a staggering thought if you sit with it long enough. We are not talking about a very long time. We are talking about a duration so incomprehensibly extended that every unit of time we use to describe human experience, years, centuries, millennia, becomes useless. So let us actually try to walk through the timeline, because the scale of this matters. Right now, roughly 10,000 years into the age of the Milky Way as a galaxy, we are in what cosmologists call the stelliferous era. Stars are forming, stars are burning. The universe is, by any intuitive measure, alive. But this era has an end date. In about 100 trillion years, that is a 1, followed by 14 zeros, the last star formation event occurs. The raw material runs out. The molecular clouds that gravity normally compresses into protostars have been used up or dispersed, and no new stellar ignition is possible. The last stars that exist at that point are the smallest, coldest, most fuel-efficient ones, red dwarfs. They burn so slowly, so carefully, that a red dwarf with a fraction of our sun's mass can live for trillions of years on its own, but even they go dark eventually. By around 100 trillion years, the last red dwarf flickers out and the stelliferous era ends. What comes next is the degenerate era. The universe is populated with stellar remnants, white dwarfs slowly cooling, neutron stars spinning down, black holes growing fat on anything that wanders too close. This era lasts an almost absurd amount of time. White dwarfs cool toward absolute zero over timescales measured in the quadrillions of years. But eventually, even they go dark, becoming black dwarfs, cold, inert stellar corpses that do nothing but drift. And slowly, over unimaginable timescales, even the protons inside ordinary matter may decay. The theoretical lifetime of a proton, if proton decay is real and we have never observed it, which is its own interesting problem, is somewhere around 10 to the power of 36 years. After that, even the cold remnants of stars dissolve into radiation and a handful of leptons. And then there are the black holes. Black holes are the last complex structures standing. By the time protons have decayed, black holes are the only things in the universe that have any meaningful gravitational influence, any capacity to do thermodynamic work, any claim to being a distinct object rather than a diffuse smear of particles. But Stephen Hawking showed us in the 1970s that black holes are not forever either. They radiate. Very, very slowly. So slowly that a stellar mass black hole takes roughly 10 to the power of 67 years to fully evaporate. And a supermassive black hole at the center of a galaxy takes closer to 10 to the power of 100 years. But they radiate. Hawking radiation bleeds the mass energy out of a black hole particle by particle, and eventually even the largest black hole in the universe completes its evaporation and disappears into a final burst of thermal radiation. 10 to the power of 100 years. Let that sit there for a moment. The current age of the universe is roughly 13.8 billion years, which is about 10 to the power of 10 years. The time it takes for the largest black holes to evaporate is 10 to the power of 100 years. That is not 10 times longer than the current age of the universe. It is not 1,000,000 times longer. The exponent itself is 90 times larger, which means we are talking about a duration that makes the current age of the universe look like the first microsecond after the Big Bang. And after that enormous, staggering, almost insulting duration, the last black hole finishes evaporating, and the universe is left with precisely nothing but a faint, cooling sea of photons, neutrinos, and gravitons spreading outward forever through an expanding space that has no structure and no future. That was supposed to be the end. Physics had a clean answer. Cosmology had a clean answer. Heat death, maximum entropy, no more story. Then Roger Penrose said, "Actually, wait. Penrose, and we will spend a proper amount of time on who he is and why his credentials demand that you take this seriously." Propose something that, when you first hear it, sounds like the kind of thing that belongs in a philosophy seminar rather than a physics paper. He proposed that the infinite far future of our universe is not the end of the story. It is mathematically and geometrically and physically the same object as the Big Bang of the next universe. That the heat death, that perfect, empty, radiation-filled final state of everything, is not a termination point. It is a transition surface, a boundary between one cosmic cycle and the next. He calls this framework conformal cyclic cosmology, and he calls each individual universe cycle an aeon. Now, before you dismiss that as metaphysics dressed up in physics language, here is the thing you need to understand. Penrose is not making a poetic argument. He is making a mathematical one. And the mathematics, as we are going to trace through carefully tonight, is rooted in ideas that are already accepted and uncontroversial in physics. Ideas about the geometry of spacetime, about the behavior of light, about what it means to measure time when there are no clocks. The radical conclusion follows from premises that very few physicists would contest individually. It is only when you put them together that the picture becomes something extraordinary. And if Penrose is right, if the mathematics holds and the physics checks out, then the radiation passing through your body right now, the cosmic microwave background that fills every cubic centimeter of space on Earth, may carry within it the faintest compressed afterglow of a universe that lived and died before ours was born. a fossil record of an entire previous cosmic history written in the temperature fluctuations of the sky. That is what we are here to understand. But to get there, we need to start with a problem that predates Penrose, a problem that has been sitting at the foundation of cosmology since the very beginning. And it has to do with why the universe started in such an absurdly improbable state in the first place. Part 2. The problem with forever. Heat death, as an ending, has a philosophical problem that most physics courses skip past because it is uncomfortable and does not have a clean resolution. The problem is this: heat death is not the universe disappearing. It is the universe continuing forever in a state where absolutely nothing happens. Think about what that actually means for a moment. The equations of physics keep running. Time, by some definitions, keeps ticking. Space keeps expanding. The photons in that final radiation bath keep traveling outward. But nothing changes. No complexity forms. No information is processed. No event of any kind occurs, because every event requires an energy gradient, a difference between hot and cold, between ordered and disordered, and heat death is defined precisely as the state where all such gradients are gone. You cannot have a fire without something to burn and somewhere for the heat to go. You cannot have any process of any kind without a difference to drive it, and heat death eliminates all differences permanently. So the universe does not end, it just becomes, for all practical and physical purposes, dead while technically continuing. And forever in this context means an actual forever, not a very long time, but an infinite duration of absolutely nothing happening in a space that keeps expanding into regions no photon will ever reach. If you are the kind of person who finds that deeply unsatisfying, you are in good company. Physicists have a word for this discomfort, though they usually dress it up more formally. The technical version of the unease is this: the equations of physics describe evolution from one state to another. They are extraordinarily good at that. Given an initial configuration of matter and energy, they can, in principle, tell you every subsequent configuration. But they have almost nothing to say about why the initial configuration was what it was, rather than something else entirely. And this is where the heat death problem connects to something much deeper, something that is actually central to understanding why conformal cyclic cosmology exists as a theory. Because the universe did not start in a random state, it started in a state that was, by any rigorous measure, extraordinarily improbable, absurdly, almost impossibly ordered. And a physics that can tell you what happens next, but cannot explain why the story started the way it did, has a significant gap in its foundations. The thermodynamic arrow of time, the reason your coffee cools and does not spontaneously reheat, the reason eggs break but do not unbreak, the reason the past is different from the future, exists entirely because entropy increases. And entropy increases because the universe began in a low entropy state. The past is ordered, and the future is disordered because we started from a point of extreme order. But here is the question that heat death, stretched out to infinity, throws into sharp relief. If the universe ends in maximum entropy, and if maximum entropy is the natural, overwhelmingly probable state for any system, then why on earth did the universe begin in the opposite state? That question has no clean answer in standard cosmology. Inflation, the rapid expansion of the very early universe, explains a great deal about the structure we observe today. It explains why the cosmic microwave background is so smooth. It explains why the universe appears geometrically flat. But it does not explain why the initial conditions that set off inflation were so extraordinarily ordered. And it does not answer the question of what selected those initial conditions from the enormous space of all possible starting points. Penrose's answer, and this is the first hint of where conformal cyclic cosmology is really pointed, is that the question might be circular, that the initial conditions are not arbitrary starting points chosen from some external menu, but the output of a previous cycle. That the universe we observe, is not the first universe, and that its improbably ordered beginning is actually the maximally disordered ending of the universe before it, transformed through a geometric process that Penrose argues makes those two states mathematically identical. That is the claim we are building toward, but to understand it, we need to spend some time at the scene of the crime, examining just how extraordinary the initial conditions of our universe actually were. Part 3. The entropy crime scene. Imagine you walk into a room and find a glass of ice water sitting on a table. The ice is not melting, it is actually reforming from liquid water into ice cubes. The room is at normal temperature. Everything is ordinary, except that this one glass of water is running backward, doing something that technically does not violate any fundamental law of physics at the microscopic level, but is so extraordinarily improbable that in any practical sense, it simply cannot happen by chance. That room is approximately the level of improbability at which our universe began, except larger by an amount that makes the glass of ice water look like a guaranteed certainty. The Big Bang did not start in a disordered state. It started in a state of extraordinary, almost incomprehensible order. And most people find this counterintuitive, because when you describe the Big Bang extreme heat, extreme density, everything compressed into a point, it sounds chaotic. It sounds like the most disordered thing imaginable. But thermodynamic disorder is not about how hot or dense something is. It is about how many microstates correspond to the macroscopic configuration you are observing. And the early universe, despite its apparent ferocity, was in a configuration that corresponds to a vanishingly small number of possible microstates. Roger Penrose worked out the numbers on this, and they are among the most jarring figures in all of theoretical physics. To specify the fine-tuning of the initial conditions of our universe, meaning to quantify exactly how special the Big Bang configuration was compared to all other possible ways the same energy could have been arranged, Penrose estimated a probability of approximately 1 in 10 to the power of 10 to the power of 123. That is not 10 to the power of 123. That is 10 raised to the power of 10 raised to the power of 123. It is a number so large that if you wrote out its digits at 1 digit per atom, the number itself would be vastly larger than the observable universe. There is no analogy that does it justice. It is simply beyond the scale of anything that can be physically instantiated as a written number. What this tells us is not that the universe was lucky. It tells us that the universe began in a configuration so special, so far from generic, that luck is not even a meaningful frame. If you selected the initial configuration of our universe randomly from all possible configurations of the same total energy, you would essentially never get what we have. The odds against it are not astronomical. They make astronomical odds look like a coin flip. Now, here is where Penrose's forensic approach gets interesting, because the source of this improbability is not what you might expect. Most people, when they think about the Big Bang as an ordered state, think about the smoothness, the fact that the early universe was remarkably uniform, that the temperature of the cosmic microwave background is the same in every direction to about 1 part in 100,000. And that smoothness does matter. But it is not the deepest source of the fine-tuning problem. The deepest source is gravity. Gravity does something unusual in thermodynamics. For ordinary matter, the high entropy state, the maximum disorder state, is one of uniform distribution. Gas in a box reaches maximum entropy when it fills the box evenly. But gravity flips this logic. When you have a large gravitating system, uniform distribution is not the high entropy state. Clumped distribution is. A universe full of matter that has collapsed into black holes is in a higher entropy state than a universe where that same matter is smoothly distributed, because gravity rewards clumping and the gravitational degrees of freedom, the ways matter can be arranged under gravity, favor collapsed structures over diffuse ones. This means the smooth early universe, which looks superficially ordered, was actually in an extraordinarily low entropy state, specifically because of gravity. It had not yet begun to clump. The gravitational entropy was nearly zero, and the endpoint, the heat-death future, full of evaporating black holes, will have extracted every last unit of gravitational entropy from the matter that once existed in our universe. Penrose has a specific geometric way of describing this. He talks about the Weyl curvature, a component of the spacetime curvature tensor that describes the tidal, shape-distorting aspects of gravity. Black holes have extremely high Weyl curvature. They warp spacetime enormously in their vicinity. The early universe, by contrast, had Weyl curvature extremely close to zero. Penrose's Weyl curvature hypothesis states that the initial singularity of a universe must have Weyl curvature equal to zero, or very close to it, and this is what defines the special, low entropy beginning state that the thermodynamic arrow of time depends on. Now here is something critical to understand. Inflation, the standard cosmological story for how the early universe got so smooth, does an extraordinary job of explaining observational data. The predictions of inflationary models match the cosmic microwave background measurements with remarkable precision. Most cosmologists support inflation, and Penrose does not deny that it works observationally. His argument is more foundational. Inflation does not explain why the pre-inflationary state had the right properties to produce the inflation we observe, and it does not change the overall probability accounting. You still need an extraordinarily special initial configuration to get the inflation off the ground. You have shifted the problem, not solved it. This is an ongoing debate. Physicists like Alan Guth and André Linde, who developed inflationary models, would contest that framing. The argument about what inflation does and does not explain for the initial conditions problem is genuinely unresolved, and it is important to say that clearly. But the entropy accounting that Penrose is doing, the calculation that the Big Bang started in a 1 in 10 to the 10 to the 123 configuration, that arithmetic itself is not seriously disputed. What is disputed is how to interpret it and what follows from it. What Penrose takes from it is this: the initial conditions cannot be arbitrary. Something must select them. And that something, in his framework, is the geometry of the previous aeon, the mathematical structure of what a heat-death universe looks like when you strip away its mass and examine it purely as a conformal geometry. We are going to get to what that means. But first, we need to meet the man who built this framework and understand why, when Roger Penrose says something in physics, even the people who disagree with him pay close attention. Part 4. The Old Man versus the Consensus. Roger Penrose is not a fringe physicist. This is worth saying plainly because when someone proposes a theory as radical as conformal cyclic cosmology, a theory that suggests our universe is one link in an infinite chain of cosmic cycles, that heat-death is a beginning rather than an ending, that we can find fossils of a previous universe in the microwave background of our sky, the natural instinct is to wonder whether this person is operating outside the boundaries of serious science. With Penrose, that instinct needs to be corrected immediately. In the 1960s, Penrose proved, mathematically and rigorously, that the formation of black holes is an unavoidable consequence of general relativity. His singularity theorems, developed in collaboration with Stephen Hawking, established that once a massive enough object begins gravitational collapse, there is no physical mechanism that can stop it forming a singularity. This was not a speculation or a hypothesis. It was a proof. It followed directly from Einstein's equations and some very general assumptions about the nature of matter. It changed the way physics understood both black holes and the Big Bang. Then, decades later, Penrose won the Nobel Prize in Physics in 2020, specifically for the discovery that black hole formation is a robust prediction of general relativity. He was 90 years old when the prize was awarded. The committee was not honoring speculative work. They were honoring work that had shaped the foundations of theoretical physics for 60 years. Penrose also developed twistor theory, an alternative mathematical framework for quantum gravity that reframes spacetime in terms of light rays rather than points, and which has had significant influence on modern mathematical physics. He wrote The Road to Reality, a 1,200-page tour of the mathematical underpinnings of physics that is considered one of the most rigorous popular science texts ever written. He is, in short, someone whose geometric intuition about the deep structure of spacetime has proven reliable in the most demanding possible environments, which makes his skepticism of inflationary cosmology interesting, even if you ultimately side with the mainstream. Penrose has been arguing for decades that inflation is incomplete as a solution to the initial conditions problem, and that the mainstream cosmology community has been insufficiently rigorous about quantifying what inflation actually explains versus what it assumes. This puts him in a minority position among cosmologists. But being in a minority position is not the same as being wrong, and in Penrose's case particularly, history suggests that his geometric intuitions about fundamental physics have a way of turning out to be correct even when they initially seem eccentric. Conformal cyclic cosmology was laid out in full in his 2010 book Cycles of Time, and it has been generating controversy and serious physics papers ever since. It is not a theory that the mainstream has accepted, but it is not a theory that the mainstream has been able to cleanly dismiss either. And the reason for that, the reason it survives serious scrutiny even when individual components are contested, is that its mathematical core rests on ideas that are themselves well-established ideas about the geometry of light, the nature of scale, and the behavior of spacetime at its boundaries. And one of those ideas is so simple and so strange that it is worth spending real time on it. It has to do with the fact that light, in a very precise and technical sense, does not experience time at all. Part 5. The first crack light has no watch. Here is something that special relativity tells us that most people know in the abstract, but have never really sat with long enough to feel the full weight of it. Photons, particles of light, do not experience time. Not experience time differently from us in the way that a moving clock runs slow. Not experience time at a different rate in the way that a clock near a black hole runs slow relative to a distant observer. Photons, travelling at the speed of light through a vacuum, have zero proper time elapsed between any two events on their trajectory. A photon emitted at the moment of the Big Bang, 13.8 billion years ago, that reaches your eye right now, that photon has experienced zero elapsed time between its creation and its detection. From the photon's perspective, if we can anthropomorphize for a moment, it was emitted and detected simultaneously. The entire history of the universe, from beginning to end, occupies no duration whatsoever from the reference frame of a particle travelling at the speed of light. Now, this is not a philosophical claim or a loose metaphor. It follows directly from the mathematics of special relativity, specifically from the definition of proper time. Proper time is the time measured by a clock that travels with an object through space-time, the time recorded on a watch strapped to that object's wrist. For massive objects moving at less than the speed of light, proper time is always positive. It always accumulates. But the formula for proper time involves a term that depends on velocity relative to the speed of light. And at exactly the speed of light, that term goes to zero. Proper time stops accruing entirely. This means photons have no internal clocks. They cannot, in any meaningful physical sense, experience duration. A photon does not age, a photon does not tick, a photon carries no watch. Now ask yourself, why does this matter for a theory about the end of the universe? It matters because of what the far future of our universe is made of. After all the black holes have evaporated, after every massive particle has either decayed or been absorbed, the universe consists almost entirely of photons. Radiation, light. Particles moving at the speed of light, which by definition experience zero proper time, which means the universe in its final state has lost all internal timekeepers. The clocks are gone. Not metaphorically gone physically, thermodynamically, irreversibly gone. The only things left are entities that the equations of physics describe as experiencing no proper time between events. This is not a small technical point. This is the crack in the wall through which Penrose's entire theory enters. If you want to define time physically, operationally define it, not just as a coordinate in some equation, but as something that can actually be measured, you need a clock. And a clock requires a massive object traveling along a time-like trajectory through space-time. A clock requires something that accumulates proper time, that can compare the reading at one moment to the reading at another. A universe made entirely of radiation has, by the fundamental rules of special relativity, no capacity to measure time at all. Not because the clocks have been misplaced, because the physical conditions that allow clocks to exist have ceased to apply. And here is where the first hint of the strange symmetry at the heart of conformal cyclic cosmology appears, though you may not see it yet in full resolution. The early universe, the fraction of a second after the Big Bang, when temperatures were high enough that all particles were effectively massless, when the energy scale was so extreme that the Higgs mechanism had not yet given mass to any particle, that universe also had no effective clocks. The electroweak symmetry was unbroken, particles were massless, and the physics of that moment was, like the physics of the far future, essentially timeless. Two universes without clocks, one at the beginning of the story and one at the end. And if the physics at both ends is structurally identical, if both are dominated by radiation, both are effectively timeless, both exist in a regime where mass plays no role and scale has no physical meaning, then maybe these two ends are not as different as they appear. Maybe, in the precise geometric language of conformal transformations, they are the same thing. But we are getting ahead of ourselves. Before we can follow Penrose through the mathematics of how he stitches end to beginning, we need to understand what it means for scale itself to disappear. Because when there are no clocks, something else vanishes too, and what vanishes is the very concept of size. Part 6. Clocks are not optional. Let us be more precise about what it means to say the far future universe is timeless, because this idea carries more structural weight than it might initially appear to. Time, in physics, is not simply a coordinate. It is not just a number you assign to events so you can put them in order. Physically, operationally, time is what a clock measures. That sounds circular until you define what a clock actually is, and then it becomes profound. A clock is any physical system that cycles or evolves in a regular, reproducible way, such that counting cycles gives you a measure of elapsed duration, a pendulum swinging, an atomic transition oscillating, a quartz crystal vibrating, a pulsar spinning. All of these are clocks because they have massive components undergoing regular motion along time-like trajectories through space-time. The word time-like is technical but important. In relativity, trajectories through space-time are divided into time-like trajectories, the paths of massive objects, which always accumulate proper time, which always move at speeds less than light, and light-like trajectories, which photons travel along, where proper time does not accumulate. The ability to define time intervals, to say that 2 seconds have passed, or 2 billion years, requires the existence of systems following time-like trajectories. It requires mass. In the far future universe, after the last black hole has evaporated and the last massive particle has either decayed or been radiated away, there are no time-like trajectories left. Everything is light-like. The universe has become a medium in which only the photon's version of existence is possible, and in that medium, the concept of elapsed time loses its physical grounding entirely. Now, you might wonder whether this matters in practice. After all, time as a coordinate still exists in our equations. We can still write down equations of motion. We can still technically call one moment earlier than another. But here is the subtlety. Without physical clocks, there is no way to calibrate those equations to anything real. The equations contain a time variable, but that variable refers to nothing that can be measured inside the universe. It becomes a ghostly placeholder, mathematically present but physically empty. And the same is true of something else. If you cannot measure time, you also cannot measure distance. Distance measurement, at a fundamental level, requires the ability to time a signal round trip, or to compare a ruler to a standard, or to count cycles of a reference oscillation.